what's up? Welcome back. So we are going to finish our discussion of statistical conclusion validity when it comes to talking about bivariate correlations. So we talked about the effect size, and generally the effect size, the larger in magnitude our correlation is, the bigger the effect, the better the predictive ability, and the more accurate those predictions will be. Now let's talk about statistical significance. And this is going to be pretty important because your homework 7 is actually going to ask you about whether or not correlations are statistically significant. Now, before we move on, statistical significance is a term that often gets very frequently misused by both psychologists and statisticians alike. And it was so bad that back in 2016, the American Statistical Association basically provided guidelines for what is an appropriate understanding of statistical significance. Now, usually when you hear people talk about what statistical significance is, they will say, oh, that's the probability that you would have gotten this result through chance. That is not correct. Statistical significance is typically something that we measure with a p-value. So a p-value is a measure of probability. And in particular, the p-value measures the following. It measures the extent to which the result we got, or one that is more extreme, is unlikely if there was actually no effect in the real world. So what this kind of means for correlation coefficients, our p-value tells us how unlikely this result would be, or a higher correlation. So let's say, for example, I get a correlation of 0.75. So a measure of statistical significance would be basically saying, what are the odds that you would get a 0.75 correlation or something even higher, something more extreme, if there was actually zero correlation in real life? So what are the odds you got that if there's actually no effect? And so we measure that with a p-value. Now, generally, larger correlations are more likely to be significant, but you want to check that p-value to be sure. The p-value will depend both on the size of the effect as well as the sample size. And this actually can create what we call questionable research practices. So something we'll talk about a little bit later, especially in the fall, is the phenomenon of something known as p-hacking. So basically with p-hacking, what happens is that you have something that is almost statistically significant, but not quite. So you've run all of your people and you find that your p-value is not quite statistically significant. So what you do, if you're p-hacking, which you should never do, you're going to run more people until it reaches significance. So you're basically gaming the system to get the result that you want. And this is a questionable research practice, and it is something that should not be followed. So if you want to figure out if a correlation is statistically significant, typically if you have a printout of significance in journal articles of correlations, so they've highlighted this correlation based on the MEL study. So here we have correlations with well-being. So we have our well-being measure, and then here we have happiness. So this highlighted correlation is a correlation between being happy and the amount of time that people were coded as being alone based on those EARs. And so this is a moderate correlation. It's a little less than 0.3, and it's, well, I don't know why it says that it's positive. It actually looks like it's negative here. I guess that was a typo in the textbook. But what this means is that people who report more time being alone report being less happy. Now, you'll notice that there's a little asterisk here. If you go down here and look at the notes, an asterisk here shows that the p-value is less than 0.05. Now, typically by convention, we set our p-value at 5%, so 0.05. It does not necessarily have to be 0.05. In fact, it's generally better to kind of base your significance level on other studies that have looked at that same effect instead of just going by convention and doing 0.05 because everybody does. But it looks like the p-value that was reported here is less than 0.05. Now, we don't actually know what that p-value is, which is kind of a problem. One of the things that has been recommended recently is that you should report p-values instead of just saying, oh yeah, they were less than 0.05. You'll also notice that we have some of these that have 2, which means that their p-value is less than 0.01. So that basically means that there's less than 1% odds that you would have gotten this correlation, or one more extreme, if there was actually no effect in the real world. So this is all based on how likely or how unlikely the evidence actually is. Now, what you will kind of notice, we do have some statistical significance with moderate correlations. So don't assume that because the correlation is not 0.5 or higher that it might not be statistically significant. In fact, it absolutely can be with these moderate correlations. Now, on the other hand, if we have a correlation of 0.01 or 0.1, odds are pretty good it's not going to be statistically significant. Now, here are a couple of things that you need to know about correlations. Correlations are basically developed by determining where the line of best fit is. So it's going to look for a line that best fits through all possible data points. And what this means is that they can be very, very sensitive to outliers. So here, we've got this one outlier here in this scatter plot. Now, follow my cursor. It should be highlighted for you. If this outlier didn't exist, this is going to be a pretty weak correlation. It's pretty flat in this regard. Now, on the other hand, because we have this outlier, our line of best fit is going to move upward, and so it's going to actually inflate the strength of the relationship and make us believe that the correlation is bigger than it actually is. Now, depending on where the outlier is, it can either inflate or deflate the strength of the relationship. And correlation coefficients are really sensitive to being dragged around by these kind of outliers. So generally, it's very, very advised that before you start reporting your data, make a scatter plot and see if any of the data look like this. See if anything out there is pulling your stats around and making you think that something is there when it actually isn't. And then be sure to report that you had an outlier, and if you removed that outlier, here's what the data actually look like. Your range of possible values will also play a role. So when you're looking at correlations, you have to be on alert for what is called range restriction. So here's kind of an example. So this is something that colleges often do. They're often going to look for a certain selection cutoff for SAT scores. So here's our original scatter plot. This is fake data of GPA and SAT scores, and you can see that there's a pretty strong positive relationship. So now let's say that we introduce a selection cutoff, and we're only going to admit people that have this SAT score or higher. Now, when you restrict that range and you look for the correlation, notice how much flatter it's become compared to the original plot with no cutoff. So if your data does not have a full range of possible values, what ends up happening is that your correlation becomes deflated and flattened as a result. So again, this is a case where looking at a scatter plot can help. And then finally, when we're talking about bivariate correlation coefficients, one of the things that you'll kind of notice in general, we are looking at a relationship between two different variables. And remember too, that we are looking for a line of best fit, which means we are trying to talk about this data with a linear relationship. So Pearson's R, your correlation coefficient, is looking at a linear relationship and trying to determine whether there is a linear relationship in your data. So if your data are quadratic or curvilinear, so if your data are not linear, if we have a curvilinear relationship or quadratic data, you are probably going to underestimate the relationship. So for example, here we have the Yerkes-Dodson law that basically looks at the relationship between arousal and performance, and it's curvilinear in nature. If I tried to use Pearson's R to develop a line of best fit through this data, I'm going to get probably something that's a horizontal flat line. And that's because this will cancel out, these 3 points will cancel each other out. This high point will be canceled out by the low point. So our line of best fit is just going to horizontally cut right through. It underestimates the data and it does not describe the data appropriately. So again, look at a scatter plot of your data. If it turns out that Pearson's R, if your data is not linear, you need to use another way to describe your means, because Pearson's R, correlation coefficients, they just want to look for lines. So we've talked about construct validity, we've talked about statistical conclusion validity, and now we're going to talk about internal validity. So internal validity is basically, can I draw a cause-effect relationship from what I've done with my research? And with correlation coefficients and correlational studies, you can't. And here's why. To be able to determine that there is a cause-effect relationship between your variables, 3 different criteria need to be met. First of all, we need to meet the principle of covariance. So as variable A changes, does variable B change? Now, correlations are fine with that. Correlations are looking at how the relationship between A and B changes. So it does meet that criterion. Where it fails is in meeting the other 2. The first is temporal precedence. So basically, the change in one variable must come before the change in the other. So the change in A must come before the change in B. Now, because we're not manipulating anything, because we're only measuring, correlations have an issue known as bidirectionality. That means that we can't tell whether A came before B or B came before A. Because we're measuring and not manipulating, we don't actually know what came first. So if we find a correlation that watching aggressive TV leads to more violence, we don't know if that's because violent people prefer violent TV or because violent TV does actually make people more violent. We can't tell. And then finally, we have the third variable problem. Is there a third variable somewhere that could account for the relationship between A and B? So generally, you want to try to rule out third variables when you can, but because we are only measuring variables A and B, and because we can't manipulate them, it's possible that a third variable can explain this relationship. And because of that, correlations, again, do not allow us to infer causation. So remember that correlation does not imply causation. Now, let's talk about external validity. What if we didn't use a random sample? Well, it's not ideal, but it doesn't make your results invalid. All you can do is, it's not necessarily a big deal if you didn't have a random sample when you're making an association claim. You do want to make sure you have enough data points though. So don't really throw out your results, just make sure that you report that we didn't have quite the sample we were hoping for, and then you just vow to do better next time. And it turns out many correlational findings do generalize, that should be generalized to different types of samples. So going back to that multitasking study, so generally what we know with our young adults is that the higher their working memory capacity is, the less time they spend multitasking. So here's a sample of older adults. Now, one of the things that we know about older adults in general is that their working memory capacity declines with age. So you'll notice that relative to our young adult sample, our older adults tend to have lower working memory capacities. But by and large, despite the fact that there are some differences between groups overall, the relationship is largely still the same. The higher your working memory capacity, the less time you're going to multitask. So now let's end by talking about moderators and how they might play a role with correlations. So for example, let's say that we were looking at team success and game attendance. So generally, the more successful a team is, the more likely that you should be attending games. Now, you would think that that's true, but there's a very interesting way that this correlation breaks down. It turns out that we have a moderating variable that Oishi and colleagues found in 2007, and that's related to mobility. So are we talking about areas with high residential mobility where people move around quite a bit? So basically you have a lot of people leaving that city and a lot of new people coming in? Or do we have people who basically have low residential mobility? They love their place so much that they never leave it. And it turns out that if you're looking at different cities with sports teams and game attendance, and in particular, this is baseball, you actually find that the correlation between sports team success and game attendance is actually moderated by residential mobility. So here we're kind of looking at game attendance for the Arizona Diamondbacks, and you can kind of see that the more winning the team becomes, the greater the attendance is. Now, what this kind of tells us is that especially for high residential mobility areas, so the Diamondbacks are in Phoenix, Phoenix experiences a lot of high residential mobility. So a lot of new people come in and they don't stay for very long, and then they move away to another city and go somewhere else, and they do this pretty frequently. High residential mobility seems to create a lot of fair weather fans. Now, on the other hand, a place like Pittsburgh, where there's low residential mobility, people love it there and they stay, we don't actually see that correlation. We actually have a pretty weakly negative relationship where there are a couple of outliers here, and I have a feeling if these outliers weren't here, this line would be pretty flat. It kind of suggests that at least in areas with low residential mobility, they don't care how the team's doing. That's a part of their city, and they love that there. So that is all I had. Be aware of the role that moderators play in changing correlational relationships, and feel free to take some time to listen to this. Let me know if you have any questions on homework number 7. And don't forget that your papers are coming up pretty soon. So be sure to get in touch with me if you have any questions. I'll see you later, and take care.